All right, so we saw that the general solution of a homogeneous linear second-order differential equation of the form on the screen is a linear combination where the solution is a form of something like C1 y1 plus C2 y2, where y1 and y2 are solutions of the linear independent set on some interval. Okay, meaning we've got essentially a quadratic differential equation, so there should be two solutions. Last section we had a conversation about whether there could be two solutions, one solution, or no solution. So this time we're kind of going forward with how do we find that both solutions from a given set of information. Okay, so reduction of order. So this is a new technique for us. Suppose y1 denotes a non-trivial solution and that y1 is defined on some interval. We would like a second solution so that we can create that linear independent set on the given interval. So if y1 and y2 are linear independent, then their quotient, y2 over y1, is a non-constant. That is, y2 of x over y1 of x is equal to u of x, or more specifically, y2 is equal to that ratio u of x times y1 of x. Okay, this function u of x that we're going to investigate here can be found by substituting y2 of x in for y of x, y1 of x, into a given differential equation. This method is called the reduction of order. Try that again. Because we must solve a linear first order differential first to find u. Okay, so let's go a simple case of given one solution is e to the x is the solution of y double prime minus y equals 0. Use reduction of order to find the second solution, y2. Okay, so our general would be y equals u of x, y1 of x equals u of x e to the x. And then we want to evaluate, we essentially want to find that y double prime from this function. So that means y prime would be u e to the x plus e to the x u prime, and y second derivative then would be u e to the x plus, and then we want to do chain rule again, but that's going to give us 2 e to the x u prime plus e to the x second derivative. And if we evaluate, so y second minus y, so u e to the x plus 2 e to the x u prime plus e to the x u double minus the y, which is u e to the x. All right, and then we want to look at trying to factor that. Well, actually, we've got some terms that can cancel out on us. So right there's u to the x, and that's u to the x, so that disappears. So 2 e to the x plus e to the x second u double. And I can factor out an e to the x, so that gives me 2 u prime plus u second. Okay, so we're going to scroll this up here. All right, so at this point, just kind of remind ourselves that we're setting that equal to 0. Well, what do we know about e to the x? E to the x is never going to be 0, so we completely ignore it. We're not worried about that. Is there some differential that'll make that true? Well, let's do a sort of a creative variable swap. Maybe rewrite this in a form that makes a little bit more, using it, that'll give us a technique that we've seen before. So let's just do a good old-fashioned swap, and let's say w is equal to u prime. All right, so that means w prime would be second derivative, and I realize all we're really doing is we're making a second order differential look like a first order differential, but that's intentional. That's on purpose. So I'm going to come over here with this. So rewriting this statement, this one, right? What we've essentially done is we've said that w prime plus 2w equals 0. All right, so let's pause and say, hey, wait, haven't we seen that before? Isn't there a differential technique that looks like that would be useful to pull up? And that's the linear method process. So that's where we have an integrating factor. So that's where the p of x equals 2, and I want e to the integral of p of x dx, right? So e to the integral of 2 dx, which is just e to the 2x. So if I multiply e to the 2x times w plus e to the 2x times 2w equals 0, that's where that application of product rule comes in. So this would be the integral of d dx of e to the 2x w equals 0. So that gives me e to the 2x w equals 0. So what does that tell me about w? It tells me that w is equal to e to the negative 2x. Okay, I'm sorry, I dropped a constant in there. Sorry, when we integrated that, we picked up a constant. So w equals c1. Why not? Okay, but we also stated that w was u prime. And let me get a little bit more room here. All right, I'm going to copy this over. Give me a second. Okay, so if I integrate that, all right, that's going to give me that u equals negative c1 over 2 e to the negative 2x plus c2, and then let's put that back into our general equation. Since y was equal to u of x e to the x, and I now have an expression for u to the x, that would give me negative c1 over 2 e to the negative 2x plus c2 e to the x, which is negative c1 over 2 e to the negative x plus c2 e to the x. Okay, so if you recall, the initial part of this conversation was that our general solution looks like yc1 y1 plus yc2 y2, right? And we started this conversation off with the fact that y1 was e to the x. So what does that tell us about y2? Right? We're not talking about the constants, we're talking about the format of the general equation. So that format tells us that the second equation, y2, has to be e to the negative x. Okay, and let's just do a quick conversation about independence. So would those be considered independent solutions or dependent solutions? We kind of explored this last lesson, but in case it's been a little while for us, that's where I want to calculate the Wronxian and just make sure that the Wronxian is non-zero. So e to the x, e to the negative x here. So derivative of e to the x is e to the x. Derivative of e to the negative x is negative e to the negative x. And then I just want to calculate the determinant. So that would be e to the x times negative e to the negative x minus e to the x times e to the negative x, which is negative e to the x plus negative x minus e to the x plus negative x. Alright, so that's negative e to the 0 minus e to the 0, which is negative 1 minus 1, which is negative 2. And the whole point is that it's not 0. So our two solutions, e to the x and e to the negative x, are independent solutions.